All right, so this week we're going to kind of pick up where we were last week. We'll finish chapter 7, and we'll start out by talking about percent yield. At least that's where we'll get to. But before we do, um, I want to kind of revisit stoichiometry a little bit here and just kind of add some more details to it. All right, so we can combine the idea of stoichiometry with polarity. So remember we talked about solutions and their concentrations and how strong they are. Well, we can mix that with these balanced chemical equations, predicting amount of product that we get, all that stuff. So, for example, we could ask something like, how many grams of solid, and you're going, where's the molarity coming in? Just be patient, don't worry. First, we'll talk about the product. We're going to get solid silver chloride. So our solubility rules say, oh, some of you just had the hackles go up on your neck. Solubility rules. Solubility rule says silver chloride is going to be a solid. But how much of this are we going to make when we'll do 0.250 liters of a 1.50 molar silver nitrate solution? I'm really working on all kinds of ideas here. I'm not giving you the formulas. I'm giving you the names. So you're going to have to write the formulas. Well, you're going to watch me write the formulas, but you get the idea. So let's see. This is going to be mixed with, and we'll just say excess. We're not going to worry how much exactly, but more than enough sodium chloride solution to react all of our silver nitrate solution. That word excess, by the way, that's a kindness that will be going away by the end of the week. So we'll talk about what to deal with when you don't know which one's excess right off the bat. All right, so, okay, there's our problem. What type of reaction is this, by the way? What do we got here? Well, it's a precipitation. It'll probably be easier to see when we write the chemical equation, but we're going to have a precipitation reaction. And so here's kind of our process. It's very similar. Stoichiometry is still involved because we're switching between compounds. Or rather, I guess it's these two compounds we're switching between. And so we know the volume of our AgNO3 solution. We need to get to moles of AgNO3. How do we do that? Molarity. Molarity will get us there. Then we got to get to moles of the product that we care about, which is AgCl. And then we got to get to grams. So we're going to have some stoichiometry in the middle. And molar mass at the end. Okay? And so this step, this is what we were talking about last week. But one thing I want to add before we get into this idea of percent yield is that any way that we have of calculating moles can get folded into stoichiometry. And right now, I double checked, I looked through the notes in the class, there's two. There's a lot more in the future, and so stoichiometry doesn't go away. But right now we can do molar mass, grams to moles, but we can also do volume of solution to moles if we know the molarity of the solution. So there's things that are dissolved in a solution, and there's a solid that we put on a mass. Okay? Or I'm sorry, a solid that we put on a balance. That we mass on a balance. All right, so what do we need here? What do we need to do this problem? Well, let's see. We're given a molarity, we're given a volume, so actually we have everything for step 1. We're going to need a balanced chemical equation for the second conversion there. Can't do stoichiometry without it, right? So you need that. I'm pretty sure we've seen this reaction before, but we'll get there. And I'm also going to need the molar mass of silver chloride. And so we use our periodic table. We look it up, and it's 1 silver plus 1 chlorine will get us 143.32 grams per mole. Okay, so nothing fancy there. You just pull out your periodic table, you just look for silver, boom, 107.9, and chlorine is 35.45. You add them up, you get that. Or Google it, whatever. So, what do we need? Okay, we can't get into the math yet because we've got this piece, but we still need a balanced chemical equation. All right, so what am I working with here? I've got silver nitrate. That's dissolved in water, so it's aqueous. I have sodium chloride as my other reactant, dissolved in water, so that is aqueous. The reaction happens. I get my, solid silver chloride, and I get whatever's left over, so sodium nitrate. And you can look at the solubility rules and see that that is so very aqueous. All right, so that's just a solid. Make that more clear. All right, and so this, perhaps now, is more clearly a precipitation reaction. Two aqueous ionic compounds gets us a solid, and then some more aqueous stuff. All right, I think we did like the net ionic equation for this and all that stuff last week, so I don't think this is a very new chemical equation, but I'm not trying to show you new chemistry here. We're just getting a new perspective on this reaction. So now we're going to do stoichiometry with it. So we're going to bring that idea in. All right, so now we've got all the pieces to do the math. And so I just start out, well, what do I have? I got 0.0250 liters of solution. It is a 1.50 moles of AgNO3 per liter. Liters cancel, all right. I'm going to get 1 mole. So now I'm on to the stoichiometry step here. So look at that, I just boom right through there. So we're on our second conversion of 3. 1, 2, 3, right in the middle here. We'll get 1 mole of silver chloride. All right, for every 1 mole of silver nitrate. We just look at our stoichiometric numbers there, coefficients. All right, and that's going to get me 2 moles of AgCl, but I need to get to grams, so I need the molar mass. I got it right there. So there's going to be 143.32 grams per mole. Okay. I carry it all through the calculation and I get 53.7 grams of silver chloride. That's what I would get. At least in theory, that's what I would get. All right. This is known as a theoretical yield. This is like everything goes right. You don't lose any, your lab partner doesn't spill anything. You get 100% conversion on the reaction. In reality, you don't get 100% of your product. There's always losses somewhere. Every time you try to filter it or isolate it or transfer glassware, some of it gets left behind. It's unavoidable. There's just going to be losses. It's the cost of doing business as a chemist. But in a perfect world, in an ideal world, you could get this. So in theory, you'd get 53.7 grams. In reality, when you do the experiment, you'll get less, sometimes much less. Sometimes you just get nothing. That's always a good day at the lab bench. Everything we've calculated up till now, everything we did last week, those were theoretical yields. Every time we were doing stoichiometry, I didn't say the magic words. This was not in our vocabulary yet, but these stoichiometric calculations are theoretical yields. This is the most you could get. In a perfect world, you would get this much, but in reality, you will get less. So we're going to build on that in a second. And just to be clear, any way of calculating moles can get us to this stoichiometric step. If I can get moles, then I can do stoichiometry. And so, like I said, we only know 2 ways right now. That's going to blow up over the course of the year as you take more and more general chemistry. Every chapter is full of at least one new way to calculate moles moving forward. Most every chapter. I think we've got all the ones that don't in the rearview mirror now. So there's a lot more of opportunities for stoichiometry to rear its head in the future. So just a heads up on that. Okay, so these are theoretical yields. That's what you could get, but no one ever does. It's like every time you adopt a pet, you think you're going to get the ideal, perfect pet. In theory, you're going to get this wonderful creature that's going to enrich your life. And in reality, you're cleaning up poop on the bathroom floor or whatever it is, wherever it is they go, the kitchen. And at this point in my life, I'm just grateful when it's just the bathroom. We got one of our dogs, and she about broke me because she had an issue where, I don't know why, she would pee on our bed. And so I had to change the sheets, and she did it twice in one day, and I got really mad. And then she pooped on the bed when I was in it. And at that point, I was out of sheets. So I was just like, and she would do it as a stress response. I had to be really calm, is what I learned. I can't get really mad at the dog for peeing on the bed, or it just gets worse. So you never know. A lot of you are thinking like, I would take that dog back. They wouldn't take her back. It just they're like, no refund. Sorry, your problem now. Nah, I didn't try to take the dog back. Now she's a happy old dog, and she hasn't peed on the bed in years. But she's getting old, so at some point it will probably happen again. Not because she's stressed, but just because it happens to everybody. You're a kid, it might happen. Everyone gets old. There's a reason. There's like kid-sized diapers, then there's adult-sized diapers. It's the same with dogs. They get old, they lose control. Anyway, you never know where I'm going to go in this class. I don't have a group to rein me in with the looks of horror on their face, so who knows what I'm going to say. I also got a new headphone set up today, so I can barely hear the stupid things I'm saying because it has noise cancellation. All right, anyway, let's reel it in here. So, theoretical is what we calculate, right? That's our theoretical yield. You do the reaction in real life, you measure it out, you see what you get on, say, the balance at the end of the day. That's your experimental yield. This is what you have actually gotten, which is tricky in this situation because you're not actually getting anything, right? We're doing computer simulation labs this year. But if you went into the lab bench and you did the experiment and you made silver chloride, and then you'd filter it, and you'd dry it, and then you'd weigh it and see how much you got. And it would be much, much less than the theoretical yield of 53.7 grams. Probably, I don't know. That's a pretty easy one to get. You probably get at least 50, maybe a little bit more. So this is, this is what you could get. This is what you do get. So how do you know what your experimental yield is on, say, a homework problem or a test problem? I tell you. I say, oh yeah, you got 15 grams. I just tell you. I tell you what your experimental yield is. But in lab, this would be something that you measure. This is something you would record. This is something that it just is what it is, and we measure it. Whereas theoretical yield, we calculate it. So we can put these ideas together and get percent yield. And so percent yield is basically how much of that theoretical yield did I get. So there's what I have, there's what I could have gotten in a perfect world. Did I get 50% of it? Did I get 70% of it? That's what percent yield is. So it's just how much of the theoretical yield did you actually get? And it's 5%. You get half of it, 50%. You get 3/4, 75% yield. And so the formula is experimental yield divided by theoretical yield times 100%, because it's got percent in the name, so we're going to multiply by 100%. All right, so that's the formula. That's what we do. And so again, this would be measured, or I just tell you, you got X amount of stuff. Theoretical yield, oh, that's the one I make you work for. That's the one you calculate. So, for example, let's say that after reacting 0.250 liters of 1.50 molar AgNO3, silver nitrate. Hopefully you're thinking this sounds familiar. Hopefully. And you react it with excess, I don't know, how about NaCl solution? You recover 37.8 grams of AgCl. What's your percent yield? Okay, well, keep in mind, we just did a lot of legwork on this reaction. The reason it looks familiar is, look at that last page, we've already calculated theoretical yield. So, theoretical was, let me get that number here real quick before I forget, 53.7 grams. And we just did that. We already did the work, right? We went from volume to moles to grams. Boom, we got it. So this was from stoichiometry. We calculated it. What's your experimental yield? How do you know what your experimental yield is? I told you. Right there. So our percent yield, we've already done most of the work for this. This is like one more step, right? This isn't too bad. So it's my experimental yield of 37.8 grams. If you think, God, I could have given you a better, sure, but it's the first time you did this reaction, so be happy with what you got. And we divide by our theoretical yield of 53.7 grams. We're going to multiply by 100%. And you punch it up in your calculator, and it comes out to be 70.4%. So that's it. So you got about 70% of what you could get, the most you could get. So that's not bad. It's not great. Yeah, it's not bad. And it really depends too on reaction to reaction. Some pharmaceuticals have atrocious percent yields because they have so many reactions along the way that there's losses all over the place. Things don't always go, 100% to completion on a reaction either. Maybe only 50% of your stuff reacts, so on and so forth. And so there's a lot of business in designing better pathways for pharmaceuticals still, especially on an industrial scale, because the more you bump this number up, that's all, the way you look at this on a manufacturing side is I have 30% losses, right? If I can cut that in half, I cut my losses in half. And in the chemical business, you're paying for the materials to make this stuff. And then when you get the wrong thing, if you don't get it all the way to completion, that's waste you're paying to dispose of. So you end up paying for something twice if it doesn't end up being what you need. If you're working, if you have an aspirin factory, you want to make as high of a percent as aspirin as possible, because everything that's not aspirin, you have to pay to truck away. It's not the 1800s. You don't get to throw it in a river anymore. Or I guess I should say it's not the 1960s. You don't get to throw it in a river anymore. Although I don't think that's been rolled back yet, but I don't know. As far as I know, you still can't throw it in a river, but maybe you can do that again. Who knows? We can make the Cuyahoga burn again for the fourth time. So that's the river, if you don't know your environmental history, that's the river that caught on fire and sparked the modern environmental movement and led to things like the Environmental Protection Agency and the Clean Water Act and the Clean Air Act, all these things. Because it was literally, generally people don't expect a river to catch on fire. Ironically, the people in the area did because it was the third time, the third time the river caught on fire. So they were a little used to it, but it made national news and kind of shook everyone else. You know, this is important. And if you don't know where the Cuyahoga River is, it's in beautiful, scenic Cleveland, Ohio. So now you know. Who knew, right? All of the environmental movement of today was started in Cleveland, Ohio. All right, so that'll do it for this section. And so we'll move forward and we are going to keep building on stoichiometry in the next video. So we're going to talk about limiting reactants. So that idea of excess, that has been a little bit of a freebie I've been throwing in. You know to calculate off this one because it's the only one I gave you numbers to. And you're just like, oh, there's just enough sodium chloride and more to do the reaction. So it just doesn't factor in. Like that's not going to decide how much product we make because this is what we're limited in. And so in the next video, we'll talk about that more, but that word excess is going away. I hope there was a kindness you didn't even know was being extended to you. But I am now chopping the olive branch. So, you know, get your parachutes ready. And we'll talk about how we handle that. That's what we'll do in the next video.